I will begin with a word of prayer once I get up here. Father, we thank you for this day again. I thank you for this class and these students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So you guys have any questions about anything before I get into it? So we're still working on determinants. And hopefully today I will explain a few more things we can do with those. I suppose it would be good for me just to mention some of their properties again, right? So like number one, the determinant of a matrix is also equal to the determinant of the transpose of the matrix. All right? That is one of the properties of the determinant. Another property of the determinant is if we're taking the determinant of like A1, A2, on out until we get to like a constant times, let's say, A sub j, and then here A sub n. So what I'm saying is you've got a constant in one of the columns, all right? You've got a constant in one of the columns. Well, you can pull that constant out. All right, you can pull that constant out. That's a property of the determinant. So this would be equal to that constant times the determinant of, the same matrix without the constant, all right? And of course, you can also do this for rows, right? Like, it's also true that, if we had like A1, CAJ down here eventually, AN, the nth row, right? I could pull that constant out, and I have the same matrix without the constant, multiplied on that jth row. So we can pull a constant out of a row or column, all right? Number four, if we can go A is like, row I plus some constant times row j, like that. If that's B, then the determinant of A is equal to the determinant of B. This is another property of the determinant. If you do that kind of row operation, it doesn't change anything. On the other hand, well, this kind of already shows you what happens with a row rescaling, right? If you do a row rescaling, that amounts to like multiplying, so we could, anyway, this is helpful. 5, if you have A is like a row swap, say the ith one swap the jth one, if that's your B, then the determinant of A is equal to minus the determinant of B. All right. Six, if we have, let's see here, A is like D1, D2, Dn. If it's a diagonal matrix, then the determinant of A is just the product of the diagonals. If our A is got diagonals D1 through Dn again, and you've got zeros down here and whatever up here, then the determinant of A is the product of the diagonals. So in other words, if it's an upper triangular matrix, the determinant is simply the product of the diagonals. Number 8, if A is equal to, d1 through dn on the diagonals, and 0's up here, and whatever down here, then the determinant of A is equal to the product of the diagonals. So in other words, if you either have upper or lower or diagonal matrix, right? Upper triangular, lower triangular, or diagonal matrix, these are super easy to calculate the determinant of. We simply multiply the product, multiply the diagonal entries together, and that gives it to us. All right? Is that window making a glare on the board? I see you guys squinting some. Yes? No? Maybe so? Let me see if some of these shades are actually functional. Let's see here if I can, come on, you can. Aha! There. That should be better. All right. And finally, last but certainly not least, I'll put it up here, number 9, the determinant of A times B is equal to the determinant of A times the determinant of B. Right? In other words, the determinant of the product is the product of the determinant. Product of the determinants. All right, so some of these are relatively easy to prove. And some of these are actually, like the proof of 9 is actually somewhat technical. Well, I'll show you the proof with the projector. I don't want to write it out. I don't think it's a good use of our time to do that. But I do want you to appreciate what's behind that proof when we look at it. All right. But before we do that, let's actually use these properties to do some calculations. Yeah. So, like example 1. Suppose we have L is 1 0 0 0 3 0 4 5 7, and let's suppose U is equal to 2 4 10 zeros down here, and 5 pi natural log of 2. Ooh, let's not do that. I'm going to make this a 0 instead, all right? So if A is equal to LU, then what's the determinant of A? So there's a smart way to work this problem, and there's a dumb way to work this problem. What's the dumb way? Let's start with that. Yeah, multiply out the matrices would be unwise. Let's not do that. I mean, we could. But this also goes to answer part of that question that you might have thought about the other day, which is why on earth are we finding an LU decomposition? Well, one of the reasons to find the LU decomposition is if you have the LU decomposition, all of a sudden calculating the determinant becomes super easy, if you know the theorems about determinants, right? Because the determinant of A is the determinant of LU, which is, by property 9, that's the determinant of L times the determinant of U, right? But using properties, let's see here, by my numbering, property 8 for this piece, 1 times 3 times 7, right? And then using property 7 for this piece, times 2 times 4 times 10. So whatever that is. 101? That can't be right. No, it's got to be bigger.
No, I was adding.
Oh, you're adding? Okay, yeah. I don't know. So that's 21, 42, 42 times 4, 168, 1680? Is that what you guys told me? Yeah, there you go. Okay, so if I give you the LU decomposition of a matrix and then ask you to calculate the determinant, be wise, all right? All right, so another theorem we can prove. If A inverse exists for a square matrix A, then the determinant of A must be non-zero. Moreover, the determinant of A inverse is actually equal to 1 over the determinant of A. This is a theorem we can easily prove from what I have already claimed. So here's the proof. We have A times A inverse is equal to the identity matrix, right? By assumption of what we mean by inverse matrix, right? By definition. But that implies that the determinant of A times the determinant of A inverse, right? I mean, excuse me, I'm jumping a step. So that says the determinant of A times A inverse is equal to the determinant of I, right? But that tells us that the determinant of A times the determinant of A inverse is equal to, well, what's this? This is 1 down to diagonals, right? So by property 6, it's a diagonal matrix. The determinant of a diagonal matrix is the product of the diagonals, but the identity matrix just has 1s on the, so the determinant of the identity matrix is just 1. Okay, so we cannot we cannot allow the determinant of A equals to 0 here, right? If the determinant of A was 0, we'd have 0 equals 1. That's not good. It's forbidden, yeah. So therefore, the determinant of A must be non-zero. And, of course, you can solve for it. The inverse, and you can solve for the determinant of A inverse also. So the determinant of A inverse apparently is equal to 1 over the determinant of A, provided the determinant of A is not equal to 0. So we now have yet another criteria on our list of criteria for invertible matrices, right? Do you guys remember what it was? What was the theorem we had? A is invertible, then, I'm sorry, let me say it a different way. The following are equivalent. DFAE, the following are equivalent. Number 1, A inverse exists. The following are equivalent. A inverse exists. Number 2, AX equals to 0 has only X equals to 0 as solution. Number 3, AX equals to B can be solved for any B, right? And this is the following are equivalent for a n by n matrix, to be clear, context here. We're talking about a square matrix. What else did we have? Do you remember? So if and only if the columns of A are linearly independent. Columns of A being linearly independent is pretty much identical to number 2 if you just understand number 2 for what it means. Remember what AX equals to 0 is? That means like x1 times column 1 plus x2 times column 2 plus xn times column n. So if we set that equal to 0, it forces x1 through xn to be 0. That's exactly linear independence of the columns. But we can add to this list now the determinant of A not equal to 0. All right? Okay, so now technically speaking, I've only showed you that if A inverse exists, that implies the determinant of A is non-zero. But before the day is done, I will give you a formula for the inverse in terms of determinant, which will supply the inverse, the converse direction to this argument. All right, and any questions before let's do another example. The other theorem I wanted to share with you guys, before I forget. If A is equal to A1 plus circle A2 plus circle plus circle A3 AK, what that notation means, guys, is that it's got A1 up here, and then it's got like A2 here, and so forth and so on. Finally, down here, A sub k. Right. So here, the A sub i's are all square, and we usually call them blocks. All right. And I'm saying zero is zero out here. All right. Zero everywhere else off the blocks. This is what's called a block diagonal matrix, all right? A block diagonal matrix. And yet another theorem of the determinant says that the determinant of a block diagonal matrix right? The determinant of a block diagonal matrix can be calculated rather elegantly. It's simply the product of the determinant of the blocks. So the determinant of a block diagonal matrix is simply the product of the determinants of the blocks. In other words, then the determinant of A is like determinant of A1, determinant of A2, determinant of AK. This one I will not prove. This is kind of a pesky one to prove, but it's fun to use. Let's look at an example. Yes, sir?
What is that plus circle? What does that represent?
This.
Oh. You aren't adding them together.
That's right. It's not addition, because I'm adding together different sized matrices. So for example, I said earlier said I said at some point, at some point earlier, I said you can't add matrices of different sizes. That's true if we limit the discussion to standard matrix addition. However, this is not standard matrix addition. This is called the direct sum of the matrices. All right, the direct sum, which is probably the answer to the question you just asked me. This is direct sum. So direct sum says you make a bigger matrix where the matrices which you're adding are simply the blocks of a big block diagonal matrix. So this is going to be a 5 by 5 matrix, you see. And it looks like this, 2, 3, 4, 5. And then down here, we got 1, 2, 3, 0, 1, 1, 0, 0, 7. All right? And I will actually write in the zeros, since there aren't too many of them for me to write. But here's the rest of the entries, all right? So, all right, if I call this one, let's say A1, and I call this A2, and I call this whole thing A, what's the determinant of A? By the theorem above, it's the determinant of A1 times the determinant of A2. Right? But let's see here. So I'll write those out. There's nothing really better than what I showed you last time for the first one. You got 2, 3, 4, 5. We just have to calculate the determinant by the rule. But A2, look at that. It's what?
7.
It's 7, right? Because it's upper triangular. So Nolan just multiplied the diagonals. You got me a 7. Cool. I mean, fine. Here, I'll show my work. 1 times 1 times 7. There you go. Are you happy? All right, so, and then that's 10 minus 12 for the 2 by 2 determinant, all times 7, which is minus 14. So there you go. That the determinant of this 5 by 5 matrix is minus 14. Now, if you had used the technique that we started determinants with and tried to use expansion by minors, this would be very bad, this example. How many terms do you have to consider for a 5 by 5 matrix if you directly expand this? So the way that would work is you would do 2 times the determinant of this 4 by 4 minus 3 times the determinant of this with all that. So you'd have 2 4 by 4 determinants to calculate. And you'd have to go from there. It would be a real pain, right? Generically speaking, the determinant of A for A n by n has n factorial summands. The 2 by 2 has 2 things you add together. The 3 by 3 we saw last class has 6 things you add together, corresponding to the 6 things that you add together with appropriate signage for the cross product. The 4 by 4 determinant has 24 terms you add together if you go directly from the Laplace expansion by minors. The 5 by 5 has 120 terms that you have to add together. Every one of those ascribing the correct plus or minus and keeping track of. It's a lot to do directly. Using properties is super important. It helps us get through calculations which we could otherwise not really have hope. Yep.
So I noticed in this example the direct sum is commutative. Is that generally true?
The direct sum is not commutative. If I have B is equal to 1, 2, 3, 0, 1, 1, 0, 0, 7, direct sum 2, 3, 4, 5, that is this matrix. And this matrix is not equal to A. Direct sum is not commutative.
The determinant of it is, I guess.
Well, yeah, the determinant, indeed, the determinant of B would also be equal to the same thing. That's true. You're right about that. Absolutely, yeah. That's okay. So that's why, in some sense, this is an addition. Some people would insist that addition be commutative. This is not commutative. Direct sum is not commutative. Unless, only in a very special circumstance would it be. But anyway. So here, let me show you a typical test question on this stuff. Sometimes I like to be able to test. Oh, there's one other theorem I still need to share with you guys. If I have A is n by n matrix, and C is a scalar, then the determinant of C times A is equal to, you fill in the blank, times the determinant of A. All right, we'll leave that blank there for a second. Let's try to think about this. Let's work it out. So what is C times A? Let's say A is equal to A1, A2, AN, which is just a quick notation for columns. All right. That's not a reserve notation for columns for me. It's just helpful for proofs to like reduce the amount of writing. Then CA is what? CA1, right? Agree? That's how we multiply, scalar multiply matrix. Every component gets multiplied. So the determinant of CA is the determinant of all that. So I'll get us started. That's C times the determinant of A1, CA2, right? I'm just using property 2 on the first column, right? Property 2 on the first column. I need to make up like a formula sheet for this chapter. There should be one page that has all of the formulas on it, right? We should have that. And then I'll put it on a shirt and sell it. Merchandising, yes. I've been meaning to make merch for a while. I think that's where the big money is. Because I mean, I make like tens of dollars on YouTube, but anyway, not much. It should eventually fund the purchase of another camera when this one breaks. Because despite the 2.5% inflation, the cost of the camera's doubled in the last 2 years or something. So it's weird how everything I buy doesn't track with that 2.5% inflation figure. Isn't that weird? It's almost like the government's lying. But they never have before. What vested interest could they have in not being honest about the state of the economy? I don't know. So that's the second one. And we just keep doing this, right? How many constants do you pull out? C to the n. So there you go. That's the answer. Fill in the blank. This will catch you off guard, but we have to put C to the n here. All right. So I'll show you a typical test question I ask to test on this stuff. Where am I? Example 3, I guess. Suppose A is 2 by 2 matrix with determinant of A equals to 3, and B is a 3 by 3 matrix with determinant of B inverse equals to 5. Find the determinant of A direct sum B. All right, so we can do. Oh, and I messed it up. I meant to put a what do I want? I'll come up with a number eventually here. 4. All right, so and to be clear, I'm talking about 4A direct sum B. All right. So the question is, what's the determinant of 4 times A, parentheses, direct sum B? So we use our theorem about blocks, which gives me the determinant of 4A times the determinant of B, right? Do you guys know that put it up here. That B is equal to B inverse inverse. So that means that the determinant of B should also be equal to 1 over the determinant of B inverse, right? Applying my previous theorem that I think I just erased. But like the determinant of B and the determinant of its inverse are reciprocal. So anyway, this is what then? 4 times what? 4 times the determinant of A, right? Because we pull out the 4. And the determinant of B is just 1 over 5, right? But the determinant of A is what? So we've got 4 times 3 times 1/5. Anybody going to stop me?
So
Yep.
You need to do 4 squared.
4 squared, why is that? Because 2 by 2, right? 2 by 2. So that has to be a 4 squared. I did that on purpose, so you see you guys are paying attention. So yes, 4 squared, I owe you a 4 squared there. Also known as 16 times 3, which is 48. So the answer here is 48 over 5. All right? And, all right. So with that, let me switch gears here and show you the proof of some of these things. And I'll try to make it quick because I'm probably not going to test you on this directly, except perhaps as like a big picture description of like what was involved. So to whom much is given, much is required. I'm not going to spend a lot of time on the proofs here, but I think it's good for you to see them because it's helpful to appreciate what is going on here in terms of what I want to get across to you is that every time we use the determinant of a product as the product of the determinants, we're using like a pretty substantial theorem. It's not that obvious a thing that's true, especially with this semester's technology. And so the proof of it rests, as many non-trivial things do in here, on the elementary matrix idea. So, by the way, while we have this out, I thought I'd show you some things. This is the picture that supports the 2 by 2 determinant being the area of this parallelogram. If you shift these triangles around, you can fill that gap in and fill this gap in, and it will eventually you can see that you get the area of this big rectangle minus the area of that little rectangle as the area of this parallelogram, which is what I claimed was true. So, yeah. It's perhaps less obvious. There's a better picture, I guess. Well, anyway, let me move past here. So here's the formula I shared with you guys last time. Woohoo! Here's how that works out. Here's how the formula explicitly works out in terms of the 3 by 3 case. You get these 6 non-trivial terms, plus, 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 minus, 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 and that is straight up the determinant formula. Although I don't recommend remembering it that way. We talked about this. This is the column. You have either expand on the row or expand on the column. And let me get past this. I don't really want to. So here is a big summary of a lot of what I said today. Maybe I missed something. I don't know. Transpose doesn't change things. This one I didn't get to. If you have any row which is 0, the determinant's 0. If you have any column which is 0, the determinant's 0. And you have linearity actually with respect to I only really emphasize the fact you can pull a constant out. But if you had a sum, you could also break it into a sum of the determinants like that, everything else being equal. That's actually, I didn't write that one out. That's new for today. We just derived this with k equals to c. I talked about this a little bit and here, and all right. Now, so the proof of the linearity pretty much rests, the proof of the linearity rule, the fact that you can break up across a sum in a particular column, It pretty much follows immediately from like the formula that I wrote down for determinant and the linearity of the formula, but that doesn't help you guys. Let me just move on. Let's see here. So we talked about this. All right, finally. So here's the building block for the determinant of the product is the product of the determinants theorem. Noticing that if you look at the elementary matrices, the determinant of a row swap is -1. The determinant of a row rescaling is the row rescaling constant. And the determinant of a row addition in this sense is just 1. And also, if you have any square matrix B and any elementary matrix E, the determinant of E times B is actually determinant of E times determinant of B. And likewise, if you have a product of elementary matrices, the determinant of a product of k-fold is the product of determinants of the k-fold determinant. The proof is just gory elementary matrix arguments, all right? And so like 1, 2, and 3 are easy enough. Let me see if I can go to talk about number 4 here. If I can find the proof of 4, that's the one that's kind of interesting. Where does 4 start? I'm too close to it. 3 to prove 5. Where's 4? Huh, that's funny. I wonder why I did that. Maybe I made it homework. Notice that 6 follows by repeated application of 5. Uh-oh, I think something's gotten lost in translation here. Maybe, just maybe, 5 is my 4, and I reformatted this and forgot to reformat the proof. Something's funny going on here. So I have B as an n by n matrix, E is an elementary matrix. E, if E is a multiplication by K, then the determinant E is K. And if you look at EB, what is it? If EB is B with some row multiplied by K, because that's what EB does. So the determinant of EB, again, is the determinant of B times K, again. So determinant of EB is equal to determinant of B. Determinant EB is determinant E times the determinant B in that case. So I'm like, basically, I'm checking this formula in the case of a row rescaling. Then the next thing I do is a row interchange. I check that this is equal if E is like a row swap. And then finally, I check that if it's a row addition, then again, we can check that the determinant EB is equal to determinant E determinant B. So basically, the proof of 4 rests on case-wise examination of the 3 different kinds of elementary matrices and proving that that identity actually holds true. I'm sorry, I need to fix the notes. Obviously, I've got like the numbering off here, but no 221 student has complained about this in previous times I've used these notes. It's almost like you guys aren't reading these proofs. I mean, I hope you aren't. Well, I don't hope that. I'm just not surprised that you aren't because I don't test on it, right? And all right, so getting to the point here, a square matrix is invertible if and only if the determinant of A is not equal to 0. So remember we proved that a matrix is invertible if it can be written as the product of elementary matrices. So now if we know that, okay, so this first part of the proof deals with the case that it's not invertible. If it's not invertible, then there are elementary matrices E1 through EK such that the row reduction has a 0 row in it. And so you've got this thing has a 0 row in it. And this, I can take the product of these determinants because they're elementary matrices by the previous proposition. So determinant of this, determinant of that, determinant of that, determinant of that. Now these are all non-zero. We got a bunch of non-zero things times the determinant of A equals the determinant of the roof of A. But roof of A has a row of zeros in it if A is not invertible. So we get 0 on this side. It forces the determinant of A to be 0 as well. So, and this argument can go both ways. So like that's if A is not invertible if and only if the determinant of A is 0. Now if A is invertible, then we can see that the reduced echelon form of A has to be the identity. Oh, determinant. Well, that's what I meant to say. And hence the determinant of the roof is 1, which is of course not equal to 0, which tells me that the determinant of A must also be non-zero. So anyway, these when I first saw these arguments, when I took this course, and my professor actually spent a couple days proving this when I took this course, this kind of course that you're taking right now. I was like, what's happening? Whoa, because it just seems so, I don't know, just all these elementary matrix arguments, they're very kind of, well, they're a little bit off-putting if you're just, an undergraduate trying to learn how to solve problems. It's like, why are you dragging me into this, Because at the end of the day, that's why I led with what I led. I just need you guys to know that the determinant of AB is the determinant of A times the determinant of B. I just want you to appreciate that when you're using that, it's all of this behind the scenes. It's quite nasty. And there's the rest of the proof. Anyway, let's see here. So here's some select examples that I'll show you, because I don't want to write them out. 1, 2, 3, 2, 4, 6, 7, 8, 9. This one, notice that row 2, right, is twice row 1. If any row is a multiple of another, we can immediately conclude determinant 0. That's another theorem. This one here, see what's going on? I kind of did this example last class, right? Basically, this is almost diagonal. It's just I need to flip these rows. Once I flip those rows, that brings a minus out here, but then I just multiply the diagonals. Wait, what? Dude, it's a minus 48. It's a good thing we're looking at this together. By the way, if you email me when you find a error in the notes, it is worth 1 bonus point. Yes, please.
Swapping the rows or columns?
Yes.
So both?
Yes.
Okay.
I mean, I was swapping rows, but if you were swapping columns, I couldn't disagree. Because we have both.
Okay.
Since the determinant is equal to the determinant transpose, determinant matrix transpose, anything I say for columns, I can also say for rows and vice versa. Because the rows of the transpose are the columns of the untransposed, right? There's that transference. But yeah, I mean, you're exactly right. We could swap the columns or we could swap the rows. Like either way, it's the same. And either way, there should be a minus over here. So, all right. This one here, what did I do? I look at this and I go, oh, that 5 is nice. It's real nice. Because see that right there? I can expand on that column. And expanding that column means that 5 is the only thing that remains. Now notice plus, minus, plus, minus. That plus minus thing I worked out last time, that puts this minus here. And then everything but the 5 is the 0, 1, 2, 0, 3, 4, 2, E. What's E coming in here for? G. Oh, I put constants in. I don't know why I did that. I guess to be weird. And then I probably expanded on the first column. Plus, minus, plus. So that's why I put a minus 2 here. The minus 5 is still there. And then everything not in there, which is the 1, 2, 3, 4, right? And that is, 10 times 4 minus 6, which is minus 20. All right. I managed to not make a sign error this time. Now, do you have to calculate it this way? The answer is obviously no. So do I mean to tell you that you can calculate the one determinant like 15 different ways and all be right? Well, if you're all doing the arithmetic correctly, yes. But if some of you make mistakes, then no, right? So will 15 people come to the same determinant? Probably not. But if 10 of you get the same one and 5 don't, then since math is governed by consensus, we have to agree on the answer of the 10, right? Well, I mean, it just stands to reason that you probably, whatever the 10 agree on. But anyway, there's arithmetic. It can't be denied. How about this question? Find values of lambda such that the matrix A minus lambda I is singular, meaning the inverse doesn't exist. And here's my matrix, 1, 0, 2, 3, 1, 0, 0, 0, 0, 2, 0, 0, 3, right? So if this is singular, we must have the determinant of A minus lambda I should be 0, all right? So here we have to work with a symbolic determinant. So I got, minus lambda I just subtracts lambda on the diagonals, like that. And then I expanded, I guess here. Not sure what I did. I think I picked up here, is there a reason that the 3 would automatically not count? Plus, minus, plus, minus, plus, minus, plus. 3 minus lambda times the determinant. And then technically, plus, minus, and then like there should be like a minus 3 times the determinant of this guy, right? Can you guys tell me what happens? Look at follow the red dot. See this? What's the deal with that 3 by 3 matrix? These guys, right? Row zeros, that means the determinant of this 3 by 3 submatrix is 0. That's why we don't have to even add the minus 3 times that. So I just kept the part that was non-zero, which is this. And then I calculate that, and lo and behold, we get this. Lambda times lambda minus 1 times lambda minus 2 times lambda minus 3. So what's the answer to my question? When is A minus lambda I singular? The answer is usually not. It's only a singular, a non-invertible matrix in 4 cases, right? The 4 cases that this matrix A minus lambda I is not invertible are when lambda is 0, when lambda is 1, when lambda is 2, or when lambda is 3. Those would make this determinant 0. All right? It will turn out a little bit later in this course that it's actually very important to be able to know when a matrix is not invertible. Actually, the matrix not being invertible is what we're going to want as we study eigenvectors, and we'll see that. Sometimes, like on your next test, you might have a question of, here's 3 three-dimensional vectors. Are they linearly independent? The simplest way to check if those 3 vectors are linearly independent is to put them in a matrix and calculate the determinant. If the determinant's non-zero, they're linearly independent. And if the determinant's 0, that means they're linearly dependent. So, yeah. Like these, for example, these 3 vectors, 1, 1, 1, 1, 0, 1, 2, 1, 2, right? Remember, this notation is sneaky notation for this vector, this vector, this vector, right? If you look at this, if you add the first 2 columns, we get the what? We get the third, right? So that means that the third column is a linear combination of the first 2. If any column is a linear combination of the other columns, determinant 0. All right? So there's that. And that brings us to Cramer's rule. Now, Cramer's rule I should write out. Oh, I'm sorry, guys. I meant to hand out the exciting attendance sheet. I'll put the lights back on here. All right. Oops. All right. So suppose we have a n by n matrix A, and suppose it's invertible. All right? In other words, suppose we've got an n by n matrix for which the determinant of A is non-zero. All right? And what I'm about to share with you is known as Cramer's rule. So if AX equals to B is system with, let's say, X equals to, I'll write it as a column for once in my life, X1, X2, Xn, all right? And A in Rn by n, such that the determinant of A is not equal to 0, then we find x1 is equal to the determinant of A1 divided by the determinant of A. Now this A1 is not the first column, guys. All right, it's something else. X2, determinant of A2 divided by determinant of A. And this goes on. Eventually we get like, X sub j is the determinant of A sub j divided by determinant of A, and so forth on down the line, x to the n, the determinant of A sub n divided by determinant of A. Where we define A sub j to be A with the jth column of A replaced with the inhomogeneous term. So like, for instance, A1 would be B, and then you got like column 2 of A all the way out to the, after the first column, the rest of the columns are unmolested. All right, they're like usual. And then like A sub n in this way is like starts out with column 1, and those are left alone all the way to get n column n minus 1. But then in the last one, you put the B. All right? So this is Cramer's rule. So before I even show you the proof of this, let's just like try it out. Let's do a simple example, see if we can use it, okay? So example, what am I on here? I can't remember. Is this example 4, 5? Where are we? 4? Cool. All right, so suppose you want to solve, let's see here, 1, 2, 3, 4, 0, 4, 5, 5, 0 times x, y, z equal to 1, 0, 1, all right? So this is my A, this is my B. Cramer's rule, so let's calculate the determinant of A. We're going to need to do that everywhere, right? Determinant of A is what? It's 1 times minus 20 plus 2 times minus 20, plus 2, I meant minus 2, plus 3 times 20. You guys check me on this, see if you get the same thing. That's weird. It's all 20s. Funny.
For that last one, is it 15?
But 3, and then this one is 4 times 5.
Minus,
There's a 0 here, though.
no,
Oh, I see what you're doing. Yeah, no.
Yeah,
Yeah.
this one.
I gotcha. So, if I haven't made a mistake, we have sorry guys, I'm having 80? 80. All right. We only need to do that once, right? The determinant of A1, what's that equal to? we're talking about the determinant of 1, 0, 1, and then the other two columns stay the same. And we also need to calculate the determinant of A2, which will be and I also need to calculate the determinant of A3. So to put Cramer's rule together for a 3x3 system, I need to calculate 4 separate 3x3 determinants, all right? So let's see here. Let's make quick work of this one. Notice this right here is super nice. So I'm going to do that one. Plus, minus, plus, minus. So I've got minus 4 times the determinant of 1, 2, 1, 5, minus 4 times 5 minus 2, minus 12 by my calculation. This one here, it just is what it is. So 1 times minus 4, minus 1 times minus 20, plus 3 times 4, I think. I think 28. If you disagree and you're sure about your disagreement, let me know. Oh, look at this. Sweet. So I'm going to expand on that guy. Plus, minus, so minus 4. Determinant of 2, 1, 5, 1. Minus 4 times 2 minus 5. I think 12. So I'll pause a second here. Do you guys calculate the same thing? Like, get the most out of class when we're doing examples like this. Don't just copy what I write. Like, work it out yourself, you know? You'll get more from the class doing that. And also you get the satisfaction knowing I'm wrong before everybody else. Could happen. Maybe I made a mistake right now on purpose, just to see if you noticed. Yeah?
I don't understand when you get like the matrices besides each determinant for like determinant A1 and A2.
Oh, that's the definition up here. So let me draw your attention. This right here is the B. See B? So I swapped out the first column with B. This one, the second one is the B.
Okay.
And the third one, there is the B. All right, so put this all together. What we got? We got to find some spots to write answer. So the answer, allegedly, is x is equal to minus 12 over 80. Y is equal to 28 over 80. And z is equal to 12 over 80, which of course we could simplify if we wanted to, but I don't want to at the moment, so you'll forgive me if I don't. There you go. We solved this 3x3 system. Now here's a question. Is this the right way to solve a 3x3 system? Is this faster or slower than doing row reduction? It is definitely slower. Yeah. It's debatable. It depends on how good you are at row reduction. If you're bad at row reduction, this is a better way because it's just stone cold formula. You just write it down and work it out, right? So sometimes engineering will teach this in like circuits as a method to solve circuits. Maybe not here, but it's been done other places for sure. But this is Cramer's rule. Now the question is, why is this true? This is a really weird, like what? Where did that come from, you know? Well, apparently Cramer, right? So I'll show you